Hello everyone, myself Brindaban Ojha from NISER Bhubaneswar. Before starting my talk, I would like to acknowledge the organizing committee of TMAG Conference to give me the opportunity to present my work in this conference. The title of my talk is Driving Skyrmion with Low Threshold Current Density in Amorphous Cobalt Iron Boron Thin Films. First, I will give some introduction about my topic. First, I will tell about the Joule-Murier interaction. The Joule-Murier interaction basically antisymmetric interaction which tries to keep two neighboring spin in a canted position. This is the Hamiltonian of this interaction, and the prerequisite of the interaction is that when a ferromagnetic layer is placed next upon a high spin coupling heavy metal, that time the this interaction arises at the interface between heavy metal and ferromagnet in the thin film, and in that case the inversion mesh also has to be also unbroken. As I told in the title slide, our work is work on the skyrmion. So one has to know what is the skyrmion. Skyrmion is basically a non-Cornelian vortex-less topologically protected spin configuration. So far, two types of skyrmion observed in magnetism. One is Needle skyrmion, another is block skyrmion. The Needle skyrmion present basically in thin film, where when Rij perpendicular to Dij. The Rij basically to the displacement vector between two neighboring spin, and block skyrmion present in the bulk material when Rij parallel to Dij. When DMI present in a system, the total energy also got modified in the system, and the total energy can be written this way, where the exchange energy always tries to keep the two neighboring spin along uh, parallel direction, and the DMI term always tries to keep the neighboring spin along perpendicular to each other. And when the energy of the system minimized, in that case the angle between two neighboring spin is around d by 2j, which is a canting angle, and in that case the dominal energy uh, also got modified by this way, and the nil wall exists in a perpendicular system when d greater than dc, and dc is this. In 2016, Luchaire et al. First shown that by taking two different kind of heavy metal, one can get a uh, additive BMI in a multilayer system, which is very useful to stable X skyrmion. The next year, in 2017, Anjan Somunarayan has shown that by taking two different kinds of heavy metal is very useful to get more tunability to tune the IDMI in the system. Now I will show some literature which is very relevant to our study. Here the OETL first show that by taking a amorphous material like cobalt iron boron, one can get very higher velocity of skyrmion in a magnetic thin film, and they have observed around 100 meter per second, which is very higher than any other system like platinum, cobalt, tantalum. By motivated their work, we have also taken the cobalt iron. We have also designed a stack or stack where we have taken cobalt iron boron as a ferromagnetic layer, and we wanted to tune the threshold current density to drive this skyrmion in our system. We have prepared this stack with DC sputtering, where the tantalum, platinum and cobalt iron boron prepared in DC sputtering, and MgO has been prepared using EVM evaporation. we have varied the cobalt iron thickness from 1.1 to 1.9 nanometer. This is the sputtering system where we have deposited our system. After depositing the system sample, we have annealed our sample at 600 degrees centigrade for 1 hour to induce the perpendicular magnetic anisotropy. We have performed the MOG microscope measurement to know the EG-axis magnetization of our samples. The samples with cobalt atom thickness 1.1 to 1.6 nanometer, they have shown the EG-axis along out of plane direction, whereas the cobalt atom thickness with 1.7 to 1.9 nanometer, they have shown the EG-axis along in plane direction. Next, we have also measured the saturation magnetization MS for all the samples. But to know the exact saturation magnetization of our system, we have plotted the MS times T with the T means with the thickness of cobalt atom, and we have fitted the experimental data with the linear line. This slope of this equation, slope of the fitting, gives basically the saturation magnetization of the sample, and the fitting and the fitted line cuts the x-axis around 0.4 nanometer, which gives the dead layer of the system. In our system, the magnetic dead layer formed due to the intermixing at platinum cobalt iron boron interface and due to oxidation at cobalt iron boron MgO interface. Next, we have also calculated the effective anisotropy constant in our system. To do that, we have first measured the saturation magnetization field, which is basically the hard axis, saturation field, and this is the saturation field. This is the K effective for all the sample, and to know where the SRT is exactly where the SRT is happening, we have plotted K effective with coeffective times T with T, and we have seen that around 1.6 nanometer the SRT is happening in our system, and we have fitted the experimental data with this linear equation to reduce the Ks, the surface anisotropy constant, and Kv of the volume anisotropy constant of our system. If you see the first two data points of our of this measurement is not fitted by this linear equation, because at lower thickness the interface degradation happens more. That's why it is not fitted by this equation. As in the previous slide I told, the SRT is happening around 1.65 nanometer, means that's why we have taken these two sample, 1.5 and 1.6 nanometer sample, to see whether there are any skyrmions present in those sample or not, because we know that a system where the total energy of the system is very low, there is a possibility to getting skyrmion in those system. So as these two sample is very near to SRT, and that's why we have taken these two sample, and we have performed the MFM measurement. While we performed in the demagnetized state, we have observed the like domain in both the sample, and after applied the magnetic field, we have observed the isolated skyrmion in both the sample. The average diameter of the skyrmion in sample S3 is around 200 to 500 nanometer, whereas the average diameter of this skyrmion for in sample S4 is around 150 to 300 nanometer. So while we performing the MFM measurement, that time we have seen that some of the skyrmion got saturated during the measurement. We perform the MFM measurement with very low moment tip, as very low moment tip has very low stray field. So, and with very low stray fields also, this skyrmion got saturated, means these samples have very low pinning side, which is very useful for to get a higher velocity of skyrmion, as while we study the skyrmion dynamics. So as I told, IDMI plays a crucial role to stabilize the skyrmion in a multilayer thin film. So here we have, that's why we have quantified the IDMI using BLS technique. In this technique, a polarized laser light is incident on the sample, and the photon magnon interaction happens. When 180 and the 180 degree backscatter photon, it passes through the Fabry-Perot interferometer and finally it collected through the detector. So when the interaction happen between photon and magnon, the Stokes and anti-Stokes line H will create in the BLX spectra to conserve the angular momentum. If there are any IDMI present in the system, then one can observe a frequency shift in between Stokes and anti-Stokes line. Here we have also observed the frequency shift delta F in our BLX spectra. Here we have kept constant in plane magnetic field at 371 millitesla, and we have varied the spin wave vector. After that, we have fitted this experimental data with this linear equation delta F, and from this slope of this fitting, we have determined the delta D effective, which is 0.4 plus 0.4 millijoule per meter square, which is very similar to previous report. Next, we have studied also the skyrmion dynamics via spin orbital torque. To study this, we have prepared this nanotrack using electron beam lithography and plasma etching technique. While we have applied a current, due to the spin Hall effect in the heavy metal, a spin current will flow perpendicular to the ferromagnetic layer. While the ferromagnetic spin polarized current will flow to this ferromagnetic layer, that this will create a torque on the spin structure, and due to this torque, this skyrmion will move in forward direction or along the current direction of the in the track. Here there is two track. This is before applied the current pulse and this is after applied the current pulse. Here we have applied a current pulse of pulse width 20 nanosecond. If you see here, when we applied the current pulse, the skyrmion moves forward and little bit shifted to downward direction because due to the gyrotropic force. And next we have also varied the current density J, and we have observed the average velocity. We have calculated the average velocity and we have observed a linear behavior. Now we have seen that we have able to move this skyrmion with very low critical current density, which is around 0.8 10 to the power 11 ampere per meter square, which is very lower than previous reports. In conclusion, we can show that the skyrmion are stabilized at very low field in platinum quadrangular MgO ester structure, and in our system very low pinning potential present, which helps to move the skyrmion with very low critical current density. From the study, we can also say that using this amorphous ferromagnetic material like cobalt iron boron, in future one can design a sample stack which will be very energy efficient. So now finally I will like to acknowledge my PhD supervisor, Professor Subhankar Vedanto, for his kind support and help and motivation throughout the work. I would also acknowledge Professor Stanislas Horvat for his kind discussion and help throughout the work, to Professor Andrew Thiavel for helping me in BLS measurement, to Dr. Sogato Molli for helping me in MFM as well as current induced skyrmion dynamic study, and to Dr. Meenakshi Sharma. I would also like to acknowledge the funding agencies DAE and CEPIPRA. Thank you.